Welcome to Deep Silicon VLSI YouTube channel. Let's dive into the question. For the below design, determine the fraction of time for which the output is logic high. This is the given design. Guys, here these are comparators. How a comparator works? Here this comparator is an op amp. It is inverting terminal. This is non-inverting terminal. If non-inverting terminal voltage is greater than inverting terminal voltage, then comparator output is logic 1. Similarly, if the non-inverting terminal voltage is less than inverting terminal voltage, then it produces logic 0. This is how a comparator works. This is very basic principle you need to understand, right? Next, guys, here the rest of the design means from here. You see here this, let's assume this is A, this is B, then guys here this is A bar, B bar, so that this is A bar into B bar and this is AB, isn't it? Yes. So here this particular OR gate output will be A bar B bar plus AB only now. That means in the simple language we can tell this portion is simply an XNOR gate. XNOR gate. Okay guys, so you can take the entire design and in place of this you can take XNOR gate so that you can land on the answer very easily. Yes. Okay, so for better understanding we are shifting to graphical representation. Location change. The design contains two comparators. The upper comparator non-inverting terminal voltage is 3 volts. Lower comparator non-inverting terminal voltage is 0 volts. So after the comparators, the rest of the circuit can be considered as XNOR gate, isn't it? Yes. Hence I have written the XNOR gate directly for better understanding. The upper comparator output is treated as A, lower comparator output is treated as B. Okay. Now we, like here you can see it is a 6 sine omega t input signal. Now we want to draw the output waveform for A and B. Later you can draw the output waveform, right? Now let's start A. Guys, here for this upper comparator non-inverting terminal voltage is 3 volts. So 3 volts, whenever the input voltage is less than 3 volts, output will be logic high. Okay, so let's mark the 3 volts. This is 3 volts. Now here particularly from this point, if you take at this, now you see this is input signal less than 3 volts means this portion. So at this portion obviously upper comparator output will be logic high. Let's say logic high. Whenever input voltage is more than 3, output will be logic 0. So output will be logic 0. And again when input voltage is less than 3 volts, output will be logic high. And this. Similarly, now it's time to discuss about lower comparator output B. Here the non-inverting terminal voltage is 0 volts. So whenever the input voltage is less than 0, then output will be logic high. That is possible in negative half cycle, during negative half cycle at this place. So during entire positive half cycle the output is 0, entire negative half cycle output is logic high. A and B, and these are inputs to an XNOR gate. You know XNOR gate, when same inputs are present, output is logic high. Let's see.
here at this place it is 1 0, different inputs, hence logic 0. From here especially here 0 0, hence output is logic high. Again 1 0, logic 0, and you see here 1 1, hence it is logic 1, logic high. Right guys, this one. Now for entire time period, let's assume this is 0 pi 2 pi, for a period 2 pi, again here the output you see logic high at this time period. Let's assume this time period as t1, and here even here also, even after this here guys, we'll get logic 0, isn't it? Yes. Now this is t2. So in a period of 2 pi, the output is high in the interval t1 and interval t2. Okay. Now here what is t2? One negative half cycle, means t2 is pi. Now what is t1 we want to know. Here see, let's assume this is theta 1 consider, and this will be theta 2. Guys, these crossover points are same, so theta 1 theta 2 are same only. So this entire period is 180. Then what will be the t1? This one, it is 180 minus 2 theta, because you need to remove this and this. So this portion will be 180 minus 2 theta. Now we want to find out what is theta. Let's say input signal. What is input signal? 6 sine omega t. At omega t is theta. See, at omega t if it is theta, then what will be the input voltage guys? It reaches 3 volts only, na? So it is 3 volts is equals to 6 sine theta. Now theta will be sine inverse of 3 by 6, which is 1 by 2, that is 30 degrees, isn't it? So you can write say pi by 6. Okay. Now here we can say the t1 is 180 minus 2 into pi by 6. Then the equivalent voltage can be 2 pi by 3. Let's say this is pi, you can get it anyway, it's a pi is here, so t1 will be 2 pi by 3. So now I am concluding the t1 time period where the output is high is 2 pi by 3 and the t2 is pi. Okay.
I hope you understand the waveform appears at the output terminal. Okay. Now according to that, guys, here if they are asking us the fraction of time for which the output is logic high, so that can be considered as t1 plus t2 by 2 pi, because the total period is 2 pi and the fraction where the output is high can be considered like a t1 and t2. What is t1? 2 pi by 3 and t2 complete half cycle, right? So pi divided by 2 pi. When you simplify, we will get 5 by 6. So guys, here for this particular design, the fraction of time over which the output is logic high is simply 5 by 6. Okay guys, thanks for watching. See you in the next video. This is Shivaram signing off. Jai Hind.